entitled Dielectrophoresis and Electrowetting as an antifouling process for antibacterial surfaces. So Stavros will start to present, and then the opponent, Alex, from control theory, or no, automation control, will oppose, and then ask some questions, and then it's up to the audience to question stuff. Right. The floor is yours.
Thanks. Thank you. Good morning, everyone. I'm going to present my master thesis from a double title degree master from KTH and Bologna University. So I'm going to introduce first the need of antibacterial surfaces and the actual devices that are working nowadays. And what is this about the project? I'm going to explore electrodynamic environment. Then I simulate some DEP for bacterial repulsion. I explore the electrowetting microenvironment, and at the end I have the conclusion. So these for antimicrobial surfaces. All around the world, we can see that there is a spreading in antibiotic-resistant bacteria. This is due to overdose practices because they are trying to apply antibacterial to viruses. Even more, we have seen that there's no more antibacterial agents anymore in the world, so it's drying up. One of the places that needed the most antibacterial surfaces are the hospitals. So they invert a lot of money in training personnel, in having personnel for cleaning surfaces, but they cannot get rid of all the surfaces and have some machines to sterilize the equipment. In fact, 10% of the Swedish surgery patients have bacteria-related infections. So this can be translated in a lot of cost and have to go back to the hospitals for retreatment. We can see that some of these infections can be seen in prosthetic infections because bacteria can survive a lot of days in surfaces. And one of the main devices that has this bacteria is in endothelial tubes and catheters. So we need some chemicals or autoclaves to sterilize these kind of devices. And sometimes it degrades the material. So if we have some bacteria, how can we get rid of them? First, we need to know how the bacteria forms. So in a typical operating theater, the table is one of the most devices that has a lot of falling surfaces. So as we can see, the mechanism of the bacteria to attach is there's a point that is a reversible point for the bacteria, but you need a lot of forces to detach from the surface. And then at the second point, there is a bacteria that is attached to the surface and is irreversible. Further then, you can see that the bacteria form some extracellular matrix and they develop in the biofilm and reproduction of them. Nowadays, we have two kinds of antibacterial surfaces. The one that release antibacterials like silver, bactericides, and the other that kill from the touch of the contact of the bacteria with the surface. From the first ones, we can see that there are some leeches. So in some cases, you can see that with time, you can have also on your body some leeches, and you don't want some chemicals on your body. And in the second one of the problems is the surface loading. The surface loading is, we have this device surface and this antimicrobial coating. All the bacteria that is attached to the surface is going to die because of the antibacterial surface. But then there's some colonized bacteria that they are going to try to get in contact with this dead bacteria, and at the end, it's going to form either a biofilm. And also the device surface is not going to work anymore because this layer. And also, we can find these multi-drug resistant organisms that are called superbugs, that they can also avoid this kind of antimicrobial. Now I'm going to talk about the idea of the project. So we have just some substrate and some electrodes without the electric layer, and we want to explore how the gradient of electric field or the surface energy, if it changes, it can affect the bacteria that is going to be in a casket. So I started with simulation in DEP. I created a microenvironment with 2 electrodes, and we wanted to know how is the fields of the electrophoretic force in the particle. So particles should have made sedimentation or drag forces go down, and if we turn on the electrode, there should be some forces, and we wanted to know qualitatively if they're going to be enough for repulse the bacteria and give a distance from the surface for keeping from attaching. As a previous works in DEP, we can see that there are some channels that you can just select the flowing of the particles. You can just accumulate or select one of the ways for particles. Also, you can see some trapping of bacteria with EDP, that is called insulator DEP. And there's also a sorting of particles and cells with this black spots, and we can see there are electrodes. So if the flowing is going from the right, the force that is applied from the electrodes push the bacteria that is affected in the other way. So they're sorting the one bacteria from the other, or particles. So I have this bacteria that I wanted to use, and I need to model it. Bacteria usually have cell wall, a membrane, and a cytoplasm. And all of these 3 layers have different conductivities and permittivities. So I need to have only one value. For that, I use a smear out the sphere approximation, where I can approximate all the values of these 3 layers in one. Done that, I have tested these electrodes with 8 micrometer of length and different values of volts from 0 to 20. But I see that the electric field was the same in all of the cases, but was changing only in the magnitudes. But the shape was the same. So I wanted to know how can I reject or attract the bacteria. The formula for the electrophoresis is that one. So we can see that it's depending on complex the electric properties and the gradient of the square electric field. And this complex, the electric, is based on the conductivity of the medium and the permittivity and the frequency that is inserted. So this part of here is called Clausius-Mossotti factor. Based on this, I have the values of E. coli and yeast, and I made this graph for seeing in which frequency areas I can see the repulsion and the attraction. So in the lower frequency range, I can see that there's a repulsion forces. Moreover, I simulated the gradient of the electric field, and I wanted to know how it feels particles if they were supposed to be at 37 micrometers. So we see that the orange lines are the electrodes, where the electrodes are situated, and the green areas are the repulsive forces. While here we can find that above the electrodes you can find attractive forces. So in order to minimize and to have more repulsion forces, we can just narrow the electrodes, but also we have to keep in mind that if we separate enough these electrodes for having more repulsive forces, we can make a gap for going bacteria in that direction. So as an advantage, we can see that there's strong repulsion forces for particles at low voltages, and with really easy surface to fabricate. But one of the problems is that it's frequency dependent. So different bacteria may require different repulsion frequencies. And also the narrow electrodes that we need to optimize the distance. So as a learning, I saw that the magnitude of force was enough to move bacteria. The frequency of the CM factor that is called Clausius-Mossotti it's not really easy to find data from other bacteria. And I also see that a thick Teflon layer of 100 nanometers only reduce completely the forces on top of the electrode, but not changing the qualitatively the electric field all around the surface. And as you can see here, there are always the holes because of the shape of the electrodes. So there is a lot of gradient in the tips of the electrodes, but here there are going to be holes of the electric gradient that is the motive to produce the force of the electrophoresis. So as a future work, I can use the chips without short circuits, determine the values for Salmonella and Pseudomonas that are bacteria that are using nowadays with the Karolinska. And COMSOL has a new feature to use particle tracing in fluids, that this could be also used in these simulations. Now I explore another method that is electrowetting to see if bacteria can be deattached. So the basic principle of electrowetting is we have a droplet with a medium and a tip that is in direct contact with it, and another electrode that is below. So if we apply a voltage with the droplet, the surface energy is going to change, and the droplet is going to try to cover as much of surface as possible. I found out that there's a wire-free configurations to not have a tip on top, so I can just have on the surface electrodes, and on top of it I have the droplet, so I can manipulate it, and I can have a better fabrication surface. So the idea on droplets is if we have particles on the droplet, if we apply some voltage, the bacteria, they are going to go down, but I can manipulate the voltage with a square wave to keep the bacteria moving, so they cannot produce this biofilm anymore. There's also some works in droplets that they can translate the droplets during the surface with this actuation. And moreover, also you can produce microstreams inside the droplet for having this movement, dynamic movement. But in our case, we are not going to use droplets. We are going to use a gasket with a medium and bacterial. So we can just put electrodes below it, apply a certain potential, and create a microdynamic environment from it. We are expecting to keep the bacteria moving by changing the surface, but we don't know really what is going to happen with it. But what we are looking for is to disturb the bacteria for preventing to bacterial adherence. As a references of what has been doing in electrowetting, we can just find that there's a transportation of droplets. There's also merge and join of droplets, as you can see here. And what I have done is I saw how these electrowetting were produced. So we change the contact angle of the droplet. I also tried with oil and the medium to see the contact angle measurements. So having that, I wanted to design my electrodes. There were a lot of configuration for it, but I took the best for our purpose. Then I create 9 cells. From the 9 cells, I have 6 that are connected to the potential and 3 that are going to work for control negative purposes. Inside of each square, we can find an array of electrodes that I will change between chips for the size of the electrode and the gaps that are between them to see how they are going to affect bacteria with the changes of these sizes. The fabrication was with these layers in gold on top of it. After that, I get the chip that we wanted with the lid top. Then I needed a gasket to to put the culture medium. So having the chip, we planned to have a gasket that can go on top of it and have leakage free. So we have this hole diameter that is fixed because they use it in the lab on Karolinska. I tried one with Oste because of the tuning properties, but I found out that there were leaks after 40 minutes. It was not enough. And I tried to use smaller pieces of Oste just to try to tune better the curing times and have least leaks on the gasket. But because of practical experiments, I just used PDMS with a really big hole on it. And it was really good adherence to the Teflon surface without leakage. So at the end, I used the PDMS. I put some electrodes on solder on the sides for practical purposes also. But I found a lot of errors in the fabrication process. There were some shortcuts, open circuits, as you can see on the right, and there were a lot of dust of the gold particles from the etching part. That was also a problem I found. What I wanted to know is which is the minimum required voltage for E-volt. So I made another setup with a silicon wafer and a copper sheet on top and a Teflon layer. I measured until I discovered that there were a Teflon breakdown. So the black line says what is the theory of the John Lippmann for electrowetting. So I discovered that there's a breakdown. So at 30 volts, we can see that there's the maximum change radically of the contact angle at that voltage. So with that, I knew that before breaking down, I can change a lot the contact angle measurements. Another problem that I found during this test was also that the Teflon breaks and they were not hydrophobic anymore. And they were formed of electrolysis because of pinholes or some breakdown of the Teflon on the surface also. I tried to avoid this breakdown by pouring some SU8 on top and then Teflon on top of the SU8. But on all of them, they failed at certain voltage, and I only found two that they were found electrowetting, but not breakdown. So, seeing this, that I think that there's a chance that there are a lot of pinholes that I cannot see to have a relationship in this table. I wanted to test how affect bacteria also these electric fields in the electrodes. So I tested, I put some a bacteria in a gasket. I washed after some period of incubation for seeing how much bacteria were attached. And I looked by the microscope in this particular order. And what I found is that after 30 minutes, not even in the active nor in the negative control surfaces, there were bacteria. So I didn't know if it was because of the electric field or not. So I tried with glass slides covered with Teflon, and also after 30 minutes, there were no bacteria attached. But I found out that it requires 24 hours for having a lot of bacteria in the surface, as you can see. So I wanted to make this alive with lab measurements, and when I take pictures while the bacteria were in the medium and the electric field was on top of it with 5 volts and 1 hertz. So after 40 minutes, I have seen a pattern in here. I also see another pictures that there were bacteria on top of the electrodes, but not on the holes, with an applied potential. That this may be cause of negative electrophoresis, but I cannot be sure for certain because of the problems of the Teflon and the electrodes. So knowing that, I need to know what is the minimum required time for having bacteria addition to the Teflon. I prepared some glass slides, and because I wanted to have less breakdown, I increase the thickness of the Teflon. I incubate bacteria for 1 hour, 16 hours, 20, and 24. I wash it away and take pictures. And after that, I count the bacteria with some software. This is how the bacteria looks like in the Teflon glass. And I took this pattern for every picture in every place. And I saw that at 20 hours, there were more bacteria than even at 24 hours. But this counted bacteria is also affected by some problem that were on the glass slides. That because of the thickness of the Teflon, I discovered that it becomes to get peeled from the glass while I submerge the glass slides. Because of the surface tensions, they rip off the Teflon, and it was easier to get off. So I measured all these bacteria just on top of the Teflon, but sometimes was not really adhered to the glass. So some observation is that the fabrication of the surface was really challenging because of the pinholes and the breakdown of the Teflon. It resulted that Teflon was really a good anti-fouling surface after 30 minutes because there were no bacteria attached at all at it. But I cannot say a good conclusion about the effect of electrowetting because I need to do more tests in a more stable microenvironment. The PMS was really leak-free. And the attachment of the Teflon can be solved by applying some promoter of adhesion that is called fluorosilane, and it can really attach to the glass. I also discovered while I was doing my test with the droplets that if I put some voltage to the droplet during some time, that I will require for having more change in the contact angle, higher voltage. So that is as a further work. I can use more addition and select better chips fabrication and more manufacturing process. So my conclusion is that this is a first step to establish new platform.